This past summer, I worked on a project at the University of Nebraska-Lincoln with the Peter Dowden Group. We worked on halide-based perovskite tin films, and formerly the group had worked with cesium lead bromide and cesium lead iodide separately, and then through natural suggestion through literature and curiosity, they got the idea to combine the two pure perovskites together and combine into a single mixed perovskite in order to investigate improved electrical properties. So the motivation behind this project comes from the increased exposure and performance of perovskites in recent years. Their long diffusion lengths and high carrier mobilities make them prime candidates for photovoltaic technologies. Their optical properties as well make them excellent for quantum dot and phasor technologies. And for industries, they're great because they're low cost and scalable, which I will talk about soon. So yeah, the goal here was to mix the two perovskites together and investigate their electrical and optical properties. So we begin with a standard wet chemical synthesis that was developed in Nebraska. Essentially, you mix some precursors together and heat accordingly. And in this process, temperature is a big variable because as you increase temperature, these perovskites are essentially crystals and they grow with temperature. And what you don't want is a quantum dot too large, so you need to control how large it becomes, and that's done through temperature control. And then once we have our perovskites in powder form, we mix them in solution with a solvent known as cyclohexane, C6H12, and this produces an ink. And then once we have an ink, we take it and put it into a refillable inkjet cartridge, as you see here, and then I can put it into a regular old printer and print out some high quality films. Up in the top corner, that is the direct mixing process we use to create the mixed perovskite. So we take a 50-50 equal mass mixture of the two pure perovskites and directly mix them together. And then over time, the halides in the solution mix and combine with each other in unequal amounts. And after some time, we get this orange solution, which is the mixed perovskite alloyed together. And we will see that a little bit later. So these are the solutions under UV light. Here is cesium lead bromide, cesium lead iodide, and the 50-50 mixture of the two. And then here are their respective films printed out. We can print on amorphous glass, which was needed for our X-ray diffraction and XPS experiments, and then we can also print on polyethylene terephthalate coated with indium tin oxide, which that's on here. So first we performed an X-ray diffraction experiment on our films. This gives us an idea of the crystal structure in our material. So we were looking for the standard orthorhombic phase for perovskites at room temperature, and that's exactly what we see with our 110 and 220 peaks that agree very well with literature. So the important thing here is that our mixed perovskite has preserved the crystal structure of perovskite, so we know we still have a perovskite, and the lattice constant shifts to a higher lattice constant as you go from bromine to iodine. And it's important to note that you may not be able to see it, but if you look really closely, you can see that the mixed perovskite is closer to bromine than it is iodine. So the fact that we have preserved the crystal structure through this mixing signifies that we have evidence of anion exchange facilitated alloy. And then using using the Share equation, we use the form factor K, the wavelength of our X-ray source, which was 1.58 angstroms, beta, which is the flow with the half max of our peaks, and theta is the drag angle, so where these peaks occur. And we determine the size of our quantum dots to be about 9 nanometers, which is very good for a quantum dot, which is supposed to be between 5 and 10 nanometers. All right, so semiconductors in general have this band structure to their electronic structure. So in the ground state, electrons typically hang out in the valence band below what's known as the Fermi level. And then when the material is excited, electrons will be promoted to the conduction band, leaving what's known as a hole or a positive charge carrier in its place. And then once the electron is done conducting electricity through the material, it falls back down and recombines with the hole and emits energy. So in photovoltaics, what's interesting is that this energy can come from light. So our material will absorb light and gain enough energy to conduct an electron, and then when that's done, it falls back down and emits energy in the form of light. And these two processes can be observed optically by using optical absorption and photoluminescence techniques. So the onset for absorption begins at the shoulders of these diagrams here, and for photoluminescence, we see the peaks over there. And as you would expect from simply the colors of our inks, we see a redshift as we go from bromine to iodine, with the mixed perovskite falling somewhere in between the two. And note again that it's closer to bromine, as well as with the photoluminescence data. The photoluminescence peaks for the mixed perovskite falls closer to bromine. So what this means is essentially this gap here corresponds to the wavelength of light, and that corresponds to the amount of energy required to exceed the gap. So what we're doing here is through halide exchange in our inks, we can fine-tune our band gap for our material. And this has important implications for all devices. So then we performed a X-ray photoemission spectroscopy experiment on our films. This tells us the chemical composition of our films. All the binding energies agree well with literature. And then we use the area under the bromine and iodine curves to determine the ratio of the halides in our mixture. And we determined this to be in a ratio of 2.4 bromine to 0.6 iodine. And the reason they're weird decimals is because we want the total to combine to 3, which is the amount of halides in the chemical formulas for these perovskites. And then we noticed there was a core level shift between the surface and the bulk of our material in the cesium 4D spectrum. So we decided to use a angle resolved photoemission, which is the exact same experiment as the previous slide, except now we take a photoemission at 0 degrees with respect to the normal, and then at 40 degrees with respect to the normal. The 0 degrees photoemission gives a greater contribution of the electric properties from the bulk of the material, and then the 40 degree spectra gives a greater contribution from the surface because it skims the surface more. And then we take a difference of the two intensities and just to separate the contributions a little bit. And we see that there's a large surface support bulk core level shift, and we can attribute this to the difference in the electronic structure between the surface of the material and the bulk. But there's still a lot of debate going on about what relevance this has in the transport properties of the material. So in the future, we hope to take transport measurements of our material. The Nebraska group was very successful alone with cesium bromide. We were having troubles with our mixed films this past summer. So in summary, the inkjet printing of our perovskites demonstrates the novel prototyping method for industrial use and its scalability. We were able to fine-tune our band gap through halide exchange, and we were able to preserve the crystal structure of our perovskites through direct mixing and through alloy. Thank you. Any questions?
From those many techniques you used, which technique did you find most interesting, or which one did you like most to use? From XRD, XPS?
I think the absorption and the photoluminescence ones were the most difficult to try to get good data from, because I had to cut up my film and put it in a tiny little device and play around with it and get it in exactly the right spot. Yeah, I think I spent the most time doing that one.
Okay. And if you would have the chance to continue, let's say, the research in this field, what would you be curious to move towards? What direction?
I would be curious to, at the beginning, I showed this kind of three-way Venn diagram of the mixtures. So maybe playing around with a mixed cation instead of mixed anion, or mixing both the cation and the anion.
Okay. Thank you very much.
One more question, Dylan.
Yeah.
Yes, I'm curious. Would it be possible to do this one using a 3D printer as well? So that you can actually grow many layers, maybe? I don't know, I'm just curious.
Yeah, so we do, we have tried printing multiple layers using our printer on top of each other.
I see.
And we wanted to investigate actually doing pure layers on top of each other, and then seeing what happens at the boundary of that. And it turns out they mix a little, but not very well, not as well as direct mixing.
I see.
And also, if I may add, I guess with 3D printer, the films may not end up so thin, as thin as they need, because it's 3D printer is more three-dimensional. So
this one is so
we may
controllable.
We may have problems, yeah, to limit the thickness of the film.
Right.
But that's an interesting idea.
Yeah.
Any other question? Thank you.